So before that we can generate this will be a given, say by God, by nature, or by other super entity, and so we have a fixed set of with x. And as we discussed before, it belongs to a big space. That means our set of hypotheses is a linear transformation of this space. So to define linear transformation, we have a vector W and additional component B. You can easily calculate how many scalars the vector W has.
How many scalars? D scalars.
Huh?
D scalars.
Yes, D. Exactly, G, W, G, factor D, and additional feature F, so formally we got G plus 1 parameters for our function. It's what we, okay. If we specify D plus 1 number, we specify the linear measure. Okay, well, maybe it's not the best notation here, so I want to clarify a bit. So if we have a scalar product of two vectors, we can also write it down like this, and formally it is sum of x wi are from 1 to d. Yes, okay. The notation from, I suppose, linear algebra. First virtual class. And also, we can say that our f(x) is this guy here, and sometimes it makes sense to specify the parameters of this function somewhere, either this way, when we have like this, or maybe formally we can say that there are also some arguments of this function. So let's write all of them together. But now we have this semicolon between the input x and the parameters. We can vary, and that will be the same for all mapping possible by the same mapping for all the whole axis. This will be our regression prediction. Given this set of hypotheses, we can finally specify the optimization problem by noting what we want to minimize. We look at the prediction of this function f hat of x I and compare it to the two y and compute the square difference between these two x. Also, it makes sense to normalize this, because if you don't normalize, you have some big number that makes little sense. If you have smaller number normalized, then it is something more understandable. We can say that it is the square difference of a typical error of a model. And also, I would say that this guy is somehow related to this risk we were thinking before, or our f defined as a linear transformation. And it's very natural to try to minimize this error from by varying W and B. We can try to find such parameters that on average we would have a benefit of the model. It's a different thing from minimizing W and B for some specific example. Yes, if you write these indexes, it's a pretty easy optimization problem. You just say that Bi would be Yi, and that's all. We would have a zero square error if you say, okay, now Bi equals to 0, now 0 vector, Bi equals to 0, or so no 0, but Yi, in this case, we would have a 0 f W, but now we want to generalize, we want to have the same W and the same B for all x's, we want to have the same function here. So typically our error would be either 0, and we would have some regression model machine learning, because we learn these parameters by minimizing this function. And we learn from this sample. Any questions? Okay. So now we have a problem. It's what we want to achieve. And now let's write the objective. I will write the objective in the matrix form. I will say that our prediction is actually a vector where each component of this vector is prediction for a specific x value. So formally we can say that this vector of x1, w plus b, x2, transpose w plus b, and so on, equal to x w, where w I united the component of w and b. Okay, agree? And x, okay, and x looks like this. It is a matrix. Each row is a row vector of the features x1 from x1 to xn, and we have additional features that equal to the constant one for continuous. Okay. Also, we compare this vector, these predictions, to the values to the true values. It's also a vector of yi to yi. And this planned error we defined in the previous slide is just a squared L2 norm of this difference. So you can say that our objective is this here. After normalization, is another also, maybe I missed this, but okay, it's clearly it's a linear regression because it's a linear vector. If you would have some linear vector, you would have a variable regression. So this is our objective, and we want to minimize it. Our goal is to minimize this guy. And I suppose most of you know that to find a candidate for an optimal, we should take the derivative with respect to parameters we have, w, and find a point such that this partial is the vector partial derivative, the gradient equals to 0. So let's do this. We basically have this square norm. It is equal to x w minus y transpose x w minus y. And because it is a square function w, we have a maximum power 2 for w. This is formula if we make all the multiplications. And basically we can say that our derivative would be, okay, if you have maybe some notation for differentiation of square functions, we take this guy, what we can do, we take divided by m, the derivative of the first guy, and the second guy, plus, for the product rule, first guy, times the derivative of the second guy. That's all, and if you take the derivative of this thing, it is a linear function of w. So we obtain just coefficients of this linear function of x. Okay, we account for the transpose, we obtain this thing. And if we look at the second term, we actually have the same thing. The derivative of it would be x w minus y transpose times x. But if you take the transpose of this, which we are interested in, we would obtain exactly the same thing. So we have a multiplier 1 divided by n before all of this, and we have the coefficient 2 because we have the derivative of the first term and the second term. Putting this all together, we obtain this formula for the derivative. Any questions? Is it too easy for you?
Not so easy, but it is
Okay.
understandable.
So now we have this thing and we want it to be 0. A 0 function. More. 0, we want each component to be 0. And so we can put here this derivative. And actually we see that we have a missed part divided by n, but okay, we can multiply both parts by n divided by 2 and obtain the previous one. On the right side is 0. It will stay 0, we have a constant multiplied by. Okay, now we open the brackets and obtain x transpose x times w minus x transpose y. We move x transpose y to the right side and obtain an equivalent equation. So our weights that should minimize this objective function should follow this equation. And so what we can do? So we have x transpose x now equals x transpose y. So we can multiply both parts by the same value. X transpose over the same matrix, x transpose x is the power minus 1, yes? Here and here is the same thing. If we multiply the left part by this inverse matrix, it just cancels the matrix we already have, and we are left with this double vector. On the right, we don't have this cancellation, so we explicitly write down this matrix here and obtain the solution if this matrix can be enlarged. It's pretty easy to calculate the computational complexity for this solution. We should just think about the dimensionality of these matrices and step by step look at the multiplication and addition. I think I would like this as an exercise if you want to do this. And instead try to make a few additional comments on what's going on. The first comment that in general we obtained a pretty good situation. We got an analytical solution to our problem. This is actually a pretty rare case in machine learning. Most of the time we would follow the same routine, with trying derivatives to be 0 and end up with our local optimum, but we would not have closed formulas like this. Okay, it's very simple. So maybe this is one reason why we study today linear regression. And get a nice solution. Basically, if you're talking about statistics, most of the problem is statistics are in a way trying to find some problem that we can solve. This is exactly a very good example of this problem. We can solve this analytically and obtain the solution to it. Actually, if you look at how good the solution is known, we have so-called Gauss theorem on how good these estimates are, and we will return to in a few hours later. But in general, we will say that we have pretty guarantees about the quality of the solution, even in this simplest case. Also, the last comment about what we should do if we have multiple possible labels, we apply the same procedure, but for each output. So suppose that we had before x and a single y here, as here is the output, and now we have x and y and y wave. And to predict y wave, we can construct a separate regression model, and formula would be the same, but now we would be putting here a vector of values of this y wave values at each specific point and all things. The generalization is pretty simple, that follows what you can expect. So the solution of separate quadratic problems similar to what we have seen here when we look at the square of this difference. Okay. Questions?